is. Okay, so let's give this a shot. Let's see what we can learn. And again, maybe just let me give you that recollection of what integrable means, because if I jump straight into a question and be like, oh, well, why are you doing it that way? So let's say maybe like recall that f a b to r is integrable if for every epsilon greater than 0, there is a partition P such that the difference between the upper and lower Darboux sums is less than epsilon. Right? Okay, and in that case, the integral we know is the unique number that is between the upper and lower sums. Case the integral is, okay, I guess let me maybe do it the way I had written it originally, which is the integral of f is going to be the supremum of the lower sums over all partitions, or the infimum of the upper sums, because those are the same thing. And we proved that those were the same thing. Or, and this follows, I mean, it's a definition. So if you want to write if and only if you can, usually I try and reserve if and only if for theorems. Some people do that with definitions, but this is a definition, right? But like I said, if you want to write if and only if, that's fine. Okay. Or alternatively, it is the only number. It is the unique number which occurs between LFP and LFP for all partitions. Okay, and these are equivalent. So if you can prove the thing on the right, the thing on the left is automatically true, and vice versa. All right. And the reason I say this, again, in theory, working with the thing on the left is a little bit easier. Working on the thing on the right is easier in practice, like if you actually need to compute an integral. Showing that you can find a number which is between every upper and lower sum is, in practice, typically much easier. And of course, in a couple of weeks, we'll learn a way easier way of doing this than having to do this by hand. But traditionally, this was, a pretty hard thing to do. That's the whole point of why we developed integration, is that, integrals are hard to compute. Okay, so here's our example. Let's do the following. So example. So let's say consider f of x, no, let's do f mapping AB. So just an arbitrary integral. And we're just going to take the function f of x equals x, right? Kind of like the easiest one that's not a constant. Do the constant on your own if you're interested, but the constant's pretty easy because the upper and lower sums are just always exactly equal to each other. So it ends up being pretty easy to do no matter what partition you choose. This is kind of like the first non-trivial one. Okay, so consider the function f of x just equals x, right? Let's show that it's integrable. Show that f is integrable. And find its integral, right? Let's find the integral. Okay. So, the graph of this thing is pretty easy to do because it's just basically a triangle. And so that gives us an idea of what the answer should be. Of course, in the case of actually doing this, we can't use the fact that we know that's the area of a triangle. We actually have to prove it, right? So let's do that. So solution. All right, first thing we got to do is we actually got to show it's integrable. And let's maybe draw a picture. The picture I'm going to draw here assumes that A and B are both positive, but that's actually not necessary for this question. But I just don't want to, draw a bunch of cases. What if A and B are both negative? Or what if, one's positive, one negative? Yeah, I don't want to care. I don't care about that. So we're just going to assume A and B are kind of both positive. Like this. Okay. So this is roughly our graph. Y is equal to X. Let me just label my axes here. And the great thing, okay, right? Look at the definition of integrable. The great thing is it says for every epsilon, so obviously we're going to start by saying let epsilon greater than 0 be given, but it says there exists a partition. So just like when we were doing epsilon delta, we get to choose what the partition should be. And the real benefit of this is that, we were talking that one of the things that could happen is your partitions could be weird. There's no reason that your partitions have to, be uniformly spaced. For example, that's generally not a requirement of partitions. But because we get to choose the partition, we might as well choose them to be uniformly spaced, right? Like make our lives easier. Like why make it harder than we have to? So suppose then that we do, right? Let me just draw a little picture here just to give you an idea of what we're going to do. And this picture is going to be really useful later too. Maybe I should try and do 4 intervals. Okay. So I'm going to, the picture I'm going to draw is I'm just going to cut this thing into 4 intervals. And let me just start drawing the upper and lower Riemann sums here for you. Okay. Yeah, so green, we'll make green the upper sum. And you can see even in our drawing that something very nice happens, right? Is that the upper sum always seems to kind of correspond to the right side of the interval, right? Like I just kind of draw the, I look at where the function is on my interval, and because the function is increasing, right? The function is strictly increasing, the supremum of the function on each interval occurs at the right endpoint. It's actually a maximum, right? By the extreme value theorem, we knew that would be true. We've got a continuous function, closed and bounded set. It's going to have a max. So the max actually occurs at the left endpoint. Let me redraw this one a little bit. It looks kind of bad. Okay. And the lower sum, in exactly the same set of reasoning, the lower sum is going to occur at the left endpoint, right? Strictly increasing. The lowest point occurs on the left side. Okay, so I'm going to try and draw in this like reddish pink thing here, roughly the height of these lower rectangles. And now something really nice happens. Okay, this is going to be a little bit hard to draw without the graph getting too busy. But if you look at this rectangle right here, notice that this red rectangle is the exact same size as the green rectangle to the left beside it, right? Because I said the partitions all have the same width. And yeah, the upper sum of the interval on the left has its maximum at the right endpoint. The lower sum for the interval to the right has its infimum at the left endpoint, but those 2 points coincide, right? The right endpoint of the left interval is the left endpoint of the right interval. It's a little confusing when you say it, but hopefully you can see that that's true. And that continues to be true all the way through, right? So if you keep looking, there almost always is a green interval on the left which cancels the red rectangle on the right. So when I subtract the green area from the red area, most of this stuff is going to cancel. So all we have to do to figure out what the sum is look and see if we can find what things are going to survive, right? And the only thing which are going to survive is the first red rectangle, the smallest red rectangle, right? Because it doesn't have a green friend, and the biggest green rectangle because it does not have a corresponding red friend, right? So the only things which will survive. So when we subtract green from red, maybe let me just do that like this. Green minus red. All right, the only thing that survives is the first red rectangle and the last green rectangle. And the last green. Okay. Basically, we're going to end up getting a telescoping series. So let's try that. Okay. That's just kind of the idea. And then again, like, okay, well, how does this help us show that the function is integrable? Well, if those are the only 2 things that survive, no matter what partition, right? That's actually not special about the partition that I draw. This will be true for any partition. The reality is that if I let my partitions become finer and finer and finer, you see that the widths of these rectangles are going to get smaller, and so their total area is going to decrease as well. And in fact, the argument is going to be that I can make that area as small as possible by allowing my partitions to become super, super fine, right? So to actually do this now, to do the math, let's divide the interval AB into n partitions. Now let's do capital N partitions of, or let's say capital N subintervals of equal size. Right, so that means I'm going to write it out for you. If you haven't done this yet, this is definitely worth doing just to convince yourself that it's true. Okay, so the formula for n, if you take the interval AB and you break it into n uniformly sized partitions, this is the formula for it, okay? It's not too hard to derive. Basically, you have to start at the left endpoint. And then what do you want to do? You just want to keep going over b minus a over n every time. Because if you take, right, what is b minus a over n? B minus a over n is the distance that you would travel if you cut the interval AB into n pieces, right? The length of that interval is b minus a, and then you divided it into n pieces. So what you're going to do is you're going to start at a, and then you're just going to go over that length, and then over that length again, and then over that length again, and over that length again, and so on and so forth, right? So this ends up being, we're going to call these things, these are the xi's. Maybe I should have said that in the beginning. This is xi, okay? And this is how we uniformly partition an interval, and it will always work, right? So if I give you a b and an a and an n, you can just use this formula if you want. You should definitely try deriving it though. It's not a formula you want to remember, but once you've derived it once, you'd be like, oh yeah, I remember how to do that. Okay. Now, since f is strictly increasing, we don't actually need the strict here, but since f is strictly increasing, the sup of f, right, on any interval xi minus 1 xi is the right endpoint, like that, right? Since you showed us this formula, yeah, you don't need to rederive it on a test. You can safely say that, like, I mean, what you can really do is you can just say, I'm choosing this partition and provide no justification for it because you get to choose it. I mean, you have to show it still works, right? Once you choose a partition, you still need to show your partition does what you want it to do, but you don't have to justify why you chose your partition as long as you can show that it works. Okay, so this is this whole idea that since I'm strictly increasing, if I take a look at what my maximum is on an interval, it must be the right endpoint, and my minimum, or my infimum in this case, must be the left endpoint, right? Okay, great. So I have all the tools that I need to compute what the Darby sums are. Maybe let me just make a little note here that delta xi, right, which remember is the length of each partition. Well, these are all just the same. Okay, so you can check this, that's certainly true. Right, so just choose one, subtract from the other, everything cancels out. The a's cancel, right? The I cancels with the I minus 1, just give you 1 left over. So the only thing that survives is b minus a over n, but we knew that. By construction, this is how this was going to work, right? Okay, so thus, the upper sum, right? So that's the sum from I equals 1 to n of the supremum times delta xi. And actually what I'm going to do is, again, because we use uniform partitions, the really nice thing is it doesn't depend on I anymore. So I can actually just take that outside of the sum. That's a real benefit of using uniform partitions. Right? Okay, and then the lower sum, you can see it's going to be exactly the same. Like the delta xi still doesn't depend on I. We're going to take it outside of the sum, and then we're going to, check what the infimum is, but we said the infimum is the left endpoint. So I'm not going to write down as much work because basically if you do the same set of steps, you arrive at exactly the same answer, except we're using now the left endpoint instead of the right endpoint. Okay, so now I'm going to subtract these. And again, I'll include a couple steps here so you can see that cancellation actually happen that I was mentioning. Okay, so we're going to get f of xi minus f of xi minus 1. Okay, and this is a telescoping series. Now maybe I should put the sum in there too. This is telescoping. Right? So if you write out a couple of terms of this, what do you get? You get like f1 minus f0 plus f2 minus f1 plus f3 minus f2. And you see that there's a bunch of, intermediate terms which cancel out. I trust that you're all can see this, but it might be worth writing out just this once, just so you can really see the cancellation that I was talking about in my picture. Right, plus dot, 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 plus. That should be capital N. And yeah, see, here's this cancellation. The fx1 here is going to cancel the fx1 here. fx2 cancels this fx2. I didn't write down the next fx3, but it's there. It'll cancel out. And everything cancels out so that the only thing which survives is f of x, negative f of x naught, right? That's the red. This is the red thing right here. So this thing, that's the first red rectangle. And then this thing here, that's the last green rectangle. So when we do all that, we get b minus a over n times f of xn minus f of x naught. But again, those are the first and last points of the partition. We know exactly what those are, right? Oh yeah, I guess I could have even simplified this further. I know what f of x is, right? F of x is just equal to x. So this is in fact just equal to b minus a squared over n like that. Okay, now obviously I haven't shown that this is less than epsilon, but b minus a is a constant, right? It's just some number. It's like 7 or something. And n, capital N, is the number of partitions I choose. So yeah, if I choose n to be big enough, right, I can make this whole thing less than epsilon. So what we'll say is, right, this was kind of like rough work. So we say choose n in n sufficiently large so that b minus a squared over n is less than epsilon, right? Now, by the work that we've just shown, so by the work above, and again, you might want to do, this stuff on the side as rough work and then write up something nice. So by the work above, UFP minus LFP is less than epsilon. So F is integrable. Okay, so I hope you're getting an appreciation that this sucks, right? That this is not the way that you want to show that functions are integrable. And next week, we will start talking about all the different, theorems that we can use to just to immediately look at a function and determine whether or not it's integrable. But for now, we're kind of stuck doing it this way. Right, so off to the side here, remember f of x is equal to x, right? So let's do x naught, for example. F of x naught, therefore, is x naught. X naught is a, right? It's the first point of the interval. So if I scroll up a bit here too, even if we just look at the definition of the partition, if I plug I equals 0 into this, I'll just get a. Yeah, exactly. And xn is b, exactly. Right? So yeah, I kind of, you see actually this entire I guess maybe this is a great point to do. Up until this point right here, okay, nothing I did used f of x equals x. The only thing I needed for this was that my function was, oh, no, oh, sorry, right until here. I got to draw my cutoff a little bit earlier. So up until here, I only used the fact that f was monotone. Monotone, technically a monotone increasing, but whatever. Okay. So what you can do very quickly, like this immediately basically gives you the proof. And I recommend that you do it before I do it. Not next Tuesday. So I'll do the proof next Tuesday. And basically the claim is every monotone function is integrable. The proof is almost exactly this. Basically, you go right up to where I cut off the line, right, where I draw the the yellow vertical line to say, up until here, I haven't used anything about the function itself. And then all you have to do instead is, again, f of x, this is still ends up being, f of b minus f of a. This whole numerator is still just a constant, right? So you just say choose n sufficiently large such that b minus a times f of b minus a divided by n is less than epsilon. Boom. You've now have that literally every monotone function is integrable, right? So big hint there for your assignment, because in your assignment, you're dealing with x squared, but you know that a and b are strictly positive. Your function is monotone, right? It's actually strictly increasing on that interval. So that'll probably help you out a lot there. Okay, so I haven't proven that, so you can't use that theorem, but I've basically given you the proof of exactly what you would do, okay? Okay, so we have to figure out the area. Now we've got a good idea of what the area should be, right? So again, if I kind of, do I have to redraw my picture? Let me just go up. Yeah, maybe I should redraw it. Let me redraw my picture. So everything here is just triangles, right? And that means that we've got, we know what the area should be. So we've got, A here, and we've got B here. So the way I would do this, right, is I would kind of imagine that I finish this triangle. That doesn't look like a great triangle, whatever. But okay, so what's the area of the big triangle? It's going to be 1/2 b squared, right? That's this triangle. Maybe let me fill it in here so you can see which triangle I'm talking about, right? And then I'm going to subtract, maybe let me put it in red. I'm going to subtract this rectangle here. And that should give me the area of the blue bit. Does everyone agree? Like that should just, if I subtract the red stuff from the white stuff, that should just give me this blue stuff. All right. So that's our guess. And of course, we can't use that because as much as we tried to motivate what we're doing from the viewpoint that it's the area under the graph, we don't actually know that our thing worked, right? So we're kind of sanity checking ourselves here. We really hope that this thing gives us 1/2 b squared minus a squared. Otherwise, we're in trouble. But at least we've got an idea of what we want to do. Okay, so how the heck do I prove this? So we need to show that, maybe let me say, put the for all up here. So for every partition, or maybe let me write that as b squared minus a squared all over 2 is like this. Or you could try and do a soup of the lower sums or an inf of the upper sums. I think that's actually probably a little bit trickier in this case. It might still be doable, but there is actually a much faster way. And I give you a very similar hint in the assignment. So what I actually want to prove, so I claim is that if P is some partition, then 2xi minus 1 is less than or equal to, what do I want here? Right, xi plus xi minus 1 is less than or equal to xi. 2xi. Okay, so again, really critical here is the fact that in a partition, xi minus 1 is less than xi, right? So I'm going to just kind of quickly, indeed, let's show that this is true. So indeed, 2xi minus 1, nope, that should be in subscript, is equal to xi minus 1 plus xi minus 1. That's going to be less than or equal to, really it's strictly less than, but we're not too worried about that. So here I'm using the fact that we know that xi minus 1 is less than or equal to xi. Again, it's actually strict, but we don't care. For the same reason. And that's equal to 2xi. Okay. Is everyone okay with that proof? Let me know if something about that bugged you. You might not see why we need that yet, but I'm going to show you in a second why that's useful. Okay. So the reason I want to use this is the following. So now what that means is I have xi minus 1 less than or equal to xi plus xi minus 1 divided by 2. So basically, I've just divided both sides by 2 here. Okay, and all right, so we're starting to see that half come in, right? That half that we know needs to show up in b squared minus a squared over half. And okay, so now what I'm going to do is I am going to, where do I want to do this? Yeah, I don't want to subtract it. Did I just multiply it? Let me just double check what I did. Oh, right. Okay, sure. So the lower sum, let's start with the lower sum. All right, so again, that's fxi minus 1. Actually, sorry, it's just xi minus 1 because we know what f is, xi minus 1 times delta x, but delta x is xi minus 1. Okay, is everyone okay with what I did there? Yell at me if not, and I'll explain it. Right, the xi minus 1 is the inf part, and then the xi times xi minus 1 is the, it's the length of the subinterval. Okay, so that's a little bit different than how I wrote it above, but it's the same thing. Okay, all right, so now we're going to use this less than or equal to this inequality here. So this is going to be less than or equal to the sum from I equals 1 to n of xi plus xi minus 1 divided by 2 xi minus xi minus 1. And what we've got here is, well, I don't want to use c plus d times c minus d, right? It's the factorization of a difference of squares. So if we simplify this for a bit, I can take the 1/2 out, sum from I equals 1 to n. And what do we get here? We're going to get xi squared minus xi minus 1 squared. This is, again, a telescoping series, right? And so the only thing which survives is the lowest term and the biggest term. So I get 1/2 xn squared minus x naught squared. And that's exactly what we wanted it to be. Okay, so we've shown that this is less, or sorry, that this number is bigger than or equal to all of the lower sums. And you can imagine you do the exact same thing, but use the other inequality. All right, so this is the sum from I equals 1 to n. This time we use xi instead of xi minus 1. Right, again, though, we're going to use that inequality above, not the circled one, but the one beside it. So this will now give us, I'm going to skip a few steps here because I did it in the lower sum. And so we've shown that this number is in fact always between the upper and lower sums, therefore it must be the integral. As we wanted. Okay, so in terms of your assignment question, the big hint here is what you'll notice. So again, think about it. I use the factorization of the difference of squares, right? I really wanted to get to this point right here, because now that I have, xi squared minus xi minus 1 squared, it's a difference of squares, but more importantly, it's telescoping, right? So what you imagine is going to be true in the assignment is you want this to end up becoming a difference of cubes, right? Because if you get xi cubed minus xi minus 1 cubed, again, it's a telescoping series. And the only thing which is going to survive is the very first term and the very last term. And if you look at the hint precisely sets you up so that you're going to get a difference of cubes, right? If you think about how to factor a difference of cubes, when you factor that term out, if you have like a cubed minus b cubed, when you factor out an a minus b, what's left over? You get a squared plus ab plus b squared. That's exactly the thing that shows up in the hint, okay? So that's what you're doing there. If you basically just replicate the steps that I've done here for f of x equals x, it shouldn't be too hard to extend this to get x squared. And in fact, to do it for any x to the n, it's a little bit more work if you want to do it for x to the n in general, but it's not too much more, right? It's not too much more at all. And there we go. There we have it. So this is a pretty long example. I did it a little bit slower, right? Just to kind of give everyone an idea of how you would actually do this. How long does this end up being? Oof. Oh yeah, it's pretty long. Okay, so there's all the work. I don't expect you to be able to read that. I just kind of wanted to, take a look at it. There's the work to show that x is integrable, right? Like the easiest function that we possibly could have had was integrable and to compute its area, right? It's tricky. Is there a case where uniform divisions won't work for the partition that we choose? So what's the word? Uniform partitions are cofinal in the collection of partitions. This is a scary word, but basically what it means is for any partition that you have, there is a uniform partition which refines it that has the same length and basically embodies the same characteristics, which means technically it's enough to use uniform partitions for everything. So there should never be a case where a uniform partition doesn't work. That doesn't mean that there aren't cases where non-uniform partitions might not be easier, if that makes sense. Like it's theoretically possible for me to give you an example of a function where a non-uniform partition is definitely the way to go. But theoretically, a uniform partition should always work. So in fact, we could have, back in the day, when we first defined integrability, we could have defined everything in terms of uniform partitions. It wouldn't have been nice. There would have been a very natural number of people who would have protested and said, well, what about non-uniform partitions? And if we had done that, I would secretly be using the fact that I know that uniform partitions are cofinal. And so that it is sufficient just to use uniform partitions. But because this is a super rigorous class, we're going to do all partitions. And then if any of you want to prove that uniform partitions are always good enough, you can do that. The proof doesn't end up being too bad. But yeah, basically anywhere you see arbitrary partition, prove that uniform partition is good enough. And the answer is basically to say, look, the important characteristics of whatever partition I need usually come down to the number of subintervals or the length of the biggest subinterval. And there's a uniform partition which does that. So, we're not too upset about it. Or there's a uniform partition which is better than that. And so it all works out in the end as well. Right. So you could actually always use uniform partitions if you want, which is why, it's how Math 135, 136 gets away with kind of doing their, or Math 136, I guess, it gets away with doing their kind of hand wavy nonsense limit definition of the Riemann sum, is precisely because they are allowed to use uniform partitions. So in 136, they only use uniform partitions, and that's why they're allowed to do it. Okay, so far so good. Anyone have any questions about this? Like I said, it's long, right? You can see it's long.
Like Tyler, can we use the like for question 2, like are we allowed to use the the summation properties of the integrals, like the upper and lower limit?
Be more precise. So those aren't necessarily like, what do you mean? You're allowed to use upper and lower sums for sure. I mean, that's definitely how the integral is defined, right?
Like, uh, like expressing one integral in terms of the sum of two other integrals, like the limit, like if their upper and lower limit matches.
Of what matches? Like the upper integral and the lower integral matching is the same as the integral?
No. Like how do I put it? It's actually in the textbook though.
Okay, well, write it. Yeah, write it down and maybe send it, post it on Piazza or something, and I can take a look at it.
Yeah, sure.
Really, though, what you want to use, I've already written down, even for question 2, is this thing right here. Okay, so question 2 is not supposed to be crazy long or crazy hard. What you know about continuity plus this is what you want.
Like I'm trying to use. Yeah, yes, I did. Like I did get to a point where I get to use this, but is it allowed to split the integral into like
additivity of domain? So you want to use it like AC? Okay. Yeah, sure. I would say if you want to use that, you can. I don't think it ends up being super important, but yeah, if you want to use it, I think that's okay.
Okay.
In fact, I'm basically going to state it.
Are we going to? Okay. We're going to talk about it right now.
Yeah, pretty much right now. So yeah, you can definitely use it.
Yeah. Okay.
So on that note, let's do this. So I'm going to call this a proposition. I don't think it's a theorem. Okay, I'm actually going to leave most of these to you. What do I want to say? F and G should be integrable. But I don't want to. Whatever. We'll just do it from scratch for each time. So if, and I think this is what Victor's talking about. So if F is integrable on AC and on CB. So you can see this is one of those ones where it would be a little bit tricky to, like, if you wanted to find these as two different functions, but these functions like morally agreed, that's just kind of a pain in the butt. So we're just going to, in the back of our heads, pretend that F is a function. We haven't really specified its domain, but you know that it's integrable on AC and on CB. Then F is integrable on their union. A, B, and the integral from A to B, F, is equal to the integral from A to CF plus the integral from C to BF, like so. Okay, so basically, and again, this should be intuitive. If you, again, think about things as kind of being the area under the graph, what are we saying? So, you've got some sort of function here, and here's A, and here's C, and here's B. And yeah, it's saying the area under the graph from A to B is the sum of the area under the graph of each of these parts, right? And again, intuitively, hopefully you're like, oh yeah, okay, I believe that. That makes sense. There's a little bit to do in terms of proving it, but right, that seems very reasonable. This has implications beyond just being a reasonable assumption. Again, we have to prove it. I'll talk about that in a second. So number 2, if F and G both, so now I am going to tell you what their domains are because it's not as important. So if F and G are integrable, then F plus G and CF are integrable for any real number C. And exactly what you think should be true is true, plus the integral of G and the integral of CF, maybe let me put that in brackets, is C times the integral of F. Okay, And again, for those of you doing linear algebra, probably if you didn't do linear algebra in the first term and you're only just kind of doing 240 now or whatever the case might be, this might mean nothing to you, but this tells you the integral is a linear operator on the vector space of integrable functions. Okay, so that's kind of a cool thing, or at least it's a linear transformation from the vector space of integrable functions to the real numbers. If that doesn't make sense to you right now, maybe just kind of like store it in the back of your brain. By the end of 240 or 223 or whatever course you're taking, that will probably make more sense. Okay, just like the derivative operator is a linear map from the set of differentiable functions to the set of less differentiable functions. That's why derivatives are a little bit nastier. Okay, if f and g are integrable, and f of x is less than or equal to g of x for all x in a b, then their integrals are also no, that's not how I've been writing the integral. F is less than or equal to the integral of g. Okay, so the integrals are monotone. This is what this is called, right? Monotonicity. I guess I should tell you what these things are called as well. So this is called additivity of domain. This is linearity of the integral. Okay, 3 here is called monotonicity of the integral, but I'm going to skip that part. And then 4, what would he call this? Is this subnormality? Oh, yeah, I'm going to call this subnormality. So if f is integrable, then the absolute value of f is integrable. And the absolute value of the integral of f is less than or equal to the integral of the absolute value of f. Okay, and this is called subnormality. Yeah, which again is some sort of like triangle inequality. If you want to think about it like that, absolutely can. I would say, yeah, more strictly speaking, it's probably a subnormal condition, but it's basically a triangle inequality. Again, if you think of the integral as being, excuse me, some sort of like really continuous sum, then this is exactly the triangle inequality for the absolute value, right? Triangle inequality kind of on the side here, right? Triangle inequality says if you add two things in their absolute value, if you want to split the absolute value, you can do that, but you have to put a less than or equal to sign, right? And you could, of course, extend this for, you know, any finite sum that you want. So if you think of the integral as being this like infinite continuous sum, then that's exactly what this is, right? This is exactly the triangle inequality. You've got a big sum on the left-hand side. You wanted to pass the absolute value onto each of the individual components of the sum. And when you do that, you can do it, but you have to put a less than or equal to sign, right? So that's exactly what this is. Okay, let me prove for you. I'm just going to prove one of them. I'm going to leave the rest as exercises. 3 is easy. 1 is non-trivial, but is not too hard. 4 is tricky. Okay, so maybe let me write that down. So 3 is simple. 1 is non-trivial, but not hard. And 4 is hard. Okay, so just for when you're trying them yourself. I don't think they have, I would just call these properties of the integral. Like limit laws, if you said limit laws to anyone, they would know what you were talking about, right? These are properties of the integral, and those aren't canonically defined. Some people might add a couple of integral laws. Some people might subtract a couple integral laws. So if you said properties of the integral, people aren't 100%. That's why these are sort of named independently. Like when we talked about the limit laws, we just kind of said limit laws, right? We didn't talk about the additive limit law or the multiplicative limit law or whatever the case is. We can, and people would know what you were talking about if you said those words. But if you just said limit laws, everyone knows what you're talking about. Here, they're given very special names precisely because there isn't a canonical set of integral laws. So you often need to be able to refer to precisely which integral law you're talking about. That's why they have different names. Right. But again, eventually, especially by the time you get to the end of the course, if you're dealing with anyone, like once you leave the context of this course, all of these properties are known and should be relatively universal. And so you can almost use them without referring to them by name. But while you're learning them, like I said, it's a great question, but there isn't a canonical set of integral laws. So yeah, we have to go name by name. Okay, let's see. Is 2 easy? Yeah, 2 is pretty straightforward. I'm going to do the harder of them. So I'm going to leave this one for you. This one's very easy. This one is, it's harder than 3, but I think it's easier than 1. Yeah. Okay, so it's harder than, like 3 is really straightforward. Like 3 is really, really simple. The moment you start, right, like you already know that f and g are integrable, so there's nothing you have to do there. You just have to compare their integrals. So literally just start writing down like the upper sum for these 2 integrals. The upper sum for f and the upper sum for g, but the upper sum for f is definitely less than or equal to the upper sum for g because f is less than or equal to g everywhere, right? And so you get that the upper sum for f is less than the upper sum of g. Then you do the same thing for the lower sum, and you're done, right? Like that's it. It's 2 lines. 1 is a little bit of work. Again, it might be tricky. Like if you're not really careful about proving 1, you could probably get away with doing it without it being too hard. But really, on your first time doing one of these proofs, you should be on the more careful side. And that's why it's non-trivial, because it just requires a couple of steps, but none of those steps are independently hard. So yeah, so I'm going to do this one just so we can kind of see how you might want to do it. Okay, so let's see. But I mean, okay, so it's very similar, I think, to the limit laws, right? Like very similar. Okay, so I'm going to prove additivity of the integral. So not of domain. Right, so we're going to show f plus g, or i.e. this is number 2, but it's the first part. So I'm going to show, so we want to show that f plus g is integrable. And the integral of f plus g is the integral of f plus the integral of g. And like I said, I think as soon as I start writing this, you can be like, yeah, that looks like the limit laws, just in terms of its proof, right? Okay, so this is what we want to prove. So what do we know? We know f and g are separately integrable, right? That's one of the hypotheses of our assumption. So let epsilon greater than 0 be given. I'm pretty sure we want to epsilon over to it. And let's say, and choose partitions P and Q such that L GQ is less than epsilon over 2. And again, I'm going to name these maybe equation 1 and equation 2. Okay. Now, one thing that I haven't explicitly said, but hopefully you're comfortable with based off our discussion from last week, is that if you refine a partition, the difference between the upper and lower sums actually gets smaller. Okay, is everyone okay with that? Because remember, when we refine partitions, the upper sums, right? Upper sums get lower and lower sums get bigger. And so if we're already looking at the difference between U and L, if I refine those partitions, they go like this. And so the difference between them actually gets smaller, right? So just like when you choose a delta, choosing a smaller delta also works. Once you've got a partition which works, any refinement of that partition will also work, right? So if you haven't convinced yourself of that, do, because we're about to use it. So basically we've got our deltas which work for F and our delta which works for G. And now I'm going to take the minimum of them, i.e. I'm going to refine them both. right? So I'm going to say now set R to be equal to P union Q so that both 1 and 2 are true. Are true for R. Okay, is everyone okay with that step? Right? Refinements will make things better, not worse. They always make things better. So if 1 and 2 are true, it's also true for R. And again, if you want to formally prove it, that's actually probably a really good exercise of just playing around a little bit with partitions. So go ahead and give it a shot if you were looking for more practice there. All right. All right. So now also note, and here we're very lucky, right, that the inequalities work out. So if I take the F plus G on our new partition R, so this is, I'm going to do it all the work for the upper sum, and then I won't do it as much for the lower sum. So this is the sup of F plus G, right, X in Xi minus 1 Xi, where the Xi's are for the partition R, times delta Xi. Now, remember, we can't split the sup up really nicely, right? It's not that the sup of F plus G is sup of F plus the sup of G. That's not true. But we get a less than or equal to sign. And that's okay. We are happy and we will take the less than or equal to. And if you'll let me kind of skip a step, I'll also distribute the sum, because hopefully you see what I'm going for here. I want to write it as the, the upper sum over F and the upper sum over G. Nope, that's got to be G. Okay, is everyone okay with that? Yeah, exactly. R is that partition. I was lazy. I should have written out that it's the R is equal to X non X1, but yeah, absolutely. Yeah, for sure. Okay, is everyone okay with that less than or equal to sign? Right, like this one. This is in the review sheet, right? It's y is the sup of F plus G less than or equal to sup plus sup of G, and generally it's not equal. So, you just have to be careful about that. But again, in our case, it works out. So in total, actually, maybe kind of let me write this with this here, just so we can kind of see it in its totality. That is the identity we have, right? And then if we do the other side, L of F plus G is greater than or equal to, sorry, this should be R. Right? And again, that's going to work out for us, right? Like we got lucky in the way that these inequalities go, because now, so what am I trying to do, right? I'm trying to show that, so thus, I'm trying to show that this thing is less than epsilon, right? But again, so my signs worked out really, really well here. And sometimes you're not lucky with signs like that. But we are today. And so we will take it and we will be happy. Plus. And voila, integrable. Okay, so again, it doesn't look exactly the same as the limit law for that, but it has this sort of similar flavor where you say, okay, listen, I know it's true for F and G separately, so I'm gonna now refine the partitions. That's like taking the min of the two deltas, and then you just do what you need to do. You add the functions in, you kind of reconfigure. In the limit case, it would have been f of x minus L and g of x minus m. Here it's a little bit different, but you just kind of reconfigure that so that you can use your epsilon over 2's out. But as we refine, could the sums actually change signs, go from positive to negative? Yeah, I don't see why not, especially if your function is like really close to 0. Yeah, it definitely could. Yeah, I don't see any reason why that. So especially if the integral is actually equal to 0, right, which is possible, then changes in your partition actually could just oscillate around 0. So for example, you know that your sum is going to be 0 to be, or if you know that your integral is going to be 0, some partitions might be like 0.01, and then as you refine it, it could become like negative 0.001, right? Like you've got a better approximation there, but you still kind of oscillated around 0. No, actually, I guess I should say no, that's not true, because you know that the upper sum will always be bigger than the value of the integral. So if the integral is 0, then the upper sums will always be strictly bigger than 0, and vice versa. So could you switch signs? Yes. So if the integral is, in that case, strictly negative, let's say. So if the integral, actually, I could probably draw something like this. So let's draw maybe a really silly example. So what if I drew something like this? So here's my function, and it's like really sharp here and then really fat down here, right? So this integral is going to definitely have a negative area, right? Because it's just way more area under the x-axis than there is above. But you know, if I'm very, is there any way I can do this? Oh yeah, okay. So let's take this partition, and you know, let's maybe do a really silly partition here. The upper sum in this case is going to look like this. Right? And so that upper sum is positive. As I refine that sum though, right? If I refine that a little bit, and maybe let's say, you know, we add another point even just here. So let's just refine it by now adding that cut. Let me try and do this in a different color. Now the upper sum looks like this. Right? Does that make sense? So you can see, like, with a really bad choice of partition, even though the integral is going to eventually be negative, your really bad choice of partition could give you a positive sum, but then as you refine, it actually switches signs. It's generally not going to oscillate back and forth, but it could definitely switch signs. Yeah. Okay. For the line of the lower sum there, yes, did I not put, yeah, it's greater than or equal to, right? Because the inf actually flips it, right? Did I miss something, LGR? Oh yeah, sorry, yeah, that should be L. Thank you. Like that. Yeah, thank you. Okay, so I've only done half the work though. I've proven that the function is integrable. Now I have to prove that its integral is what I want it to be, right? Okay, so let me see. Okay, yeah, so how do we want to do this? So I know that, yeah, that should be fine. So we know that UF plus G of P, so I'm just, because now I'm doing the integral, okay? So a P and R are not the same as they were before. It's an arbitrary partition P. This is going to be less than or equal to UFP plus UGP for all P. Okay, so if I take the sup over partitions P, the supremum is going to preserve that, right? We know that's true. And because we know that both of the functions are integrable, the sup is actually going, oh, sorry, the inf. What am I doing? Somebody's going to yell at me there. Obviously, it's inf. let me make sure I didn't do something stupid here. So I know that that's always less than or equal to that. Now, if I take the infimum over that, yeah, that should still be true, right? There's no way that that should change. Yeah, okay, yeah, I'm convinced that that's true. Okay, and again, because our function is integrable, these are actually equal to the values of their corresponding integrals. So this is the integral of f plus g. This is the integral of f, and this is the integral of g. Okay, now that doesn't give us what we want. It does look a little sus. Let me think about it a little bit. Let me just finish this off, and then I'll come back and we'll try and prove it. And then so conversely, but it definitely does look sus. So I do want to look at it again, but let me just finish writing this out. So now if I soup, it should be preserved. So I want soup here, LFP plus soup, LGP. These proofs always go longer than I think they're going to go. And so I end up spending way longer than I feel like I should on them. This is greater than or equal to the integral of f plus the integral of g, and then both inequalities should give us equality. All right, now let's think about this. So let's check whether or not this actually makes sense. Okay, so I've got UFG plus P, and that's always going to be less than or equal to that. So if the left-hand side is always less than or equal to the right-hand side, and then I take the infimum, right, there's no way that it could get bigger. Right, so the only question that we're worried about is oh yeah, no, you're right. This is definitely sus, because what I would have needed to do is the following. I would have needed to do this first, right? If I were really doing it instead of like distributing it across. But then when I take the inf of the sum, I would get a greater than or equal to sign here, right? Yeah, so that's actually not okay. We can't do that. If it was the soup, I would be okay, but it's the inf, so I'm not okay. Why we can't use it? What do you mean? Because you're not limiting over, like, what is a limit, right? When you're limiting over partitions, that's a different thing. We don't know how to limit over partitions. Okay, I'm gonna have to fix this. I'm pretty sure I know how, but I'm gonna need the break to do it just so that I don't give you. So, okay, so we're gonna erase this. Erase our shame so that nobody can see it. Yeah, I'm pretty sure I know how to fix this, but let me do it over the break. That way I can mess around with it and do my rough work so you don't have to see it. And we'll come back and I will fix this for you then, okay? But yeah, Ty, what do you mean about using the limit for the Riemann sum?
Yeah, so you said something about in MAT136, they use the, I think, is it the limit when trying to calculate a Riemann sum? So, yeah. So do you mind clarifying that point?
Yeah, okay, so the way they do it, so first of all, they define, like, they don't define, Riemann sums are different than Darboux sums, right? So you have to talk about tagging when you do a Riemann sum. And what they just do is they say all partitions are uniform. So they can't have different sizes. So all partitions are uniform. And then they take a limit as the number of subintervals goes off to infinity, right? And this is not allowed at all. Because how do you take a limit over partitions, right? We don't know how to do that. We know how to take limits as like real numbers approach other real numbers. And later in this course, we'll see how to take limits of like sequences, which are functions from the natural numbers to R. But we don't know how to take limits of functions of partitions, right? So that's what it is. If you think about this thing as being a function in the P variable, right, that's fine. But we don't know how to take limits over the space of partitions. And it is possible, but it's much more complicated, in part because it's not totally ordered. What I mean by that is, in the real numbers, if I give you an X and a Y, X is always either equal to Y, or it's bigger than Y, or it's less than Y, right? One of those three things is always true. So you can always compare X and Y. So you know that X is bigger or X is smaller or they're equal. But it's not true for partitions, right? If I give you a partition P and a partition Q, you don't know which of those partitions is bigger. You might get lucky and one is a refinement of the other, but as a general rule, you can't compare them at all. So how do you now take how do you take limits of partitions if you don't know how to get from one partition to the next partition, right? You kind of have to stay within a family of things that can be compared in order to be able to actually take a limit. And there's a way you can get around this even with uniform partitions. But generally speaking, if you're just taking a limit as the length of or as the number of partitions goes off to infinity, then you can't, strictly speaking, do that. Again, there is a way of formally getting around it, but it's actually quite complicated. So you can't do that. The reason why they do it in 136 is they're not trying to be rigorous. They're just trying to give students a feel for, we've taken this approximation. We believe that the approximations get better as we take more subintervals. And so let's take a limit as we take more subintervals, and that should give us the actual value of the integral, right? So that limit for them is very informal and consequently completely and total nonsense. Like I said, there is a way that we can formalize it. There is a way that we actually could define things using limits in this class, but it's generally not how analysts do it because it's actually tricky and it requires a little bit of, and when I say a little bit, I mean, it takes a lot of work to actually set up. So that's what we mean. Does that make sense? Cool. Okay. So let's take a little break. Yeah, no problem, no problem. Let's take a little break here. So I've got, 10:17 or something. So we'll come back at 10:27. I'm going to work on this while we're gone, see if I can't quickly fix this proof, because you're right that I can't do that if thing. That doesn't make sense. So I'll fix that, and then I will hopefully when we come back have the second part of this proof ready for you. And then what are we doing? Are we doing measure? Oh yeah, and then we're doing measure, which will be a fun thing that'll you'll get to see in a bit. Okay, so 10 minutes, 10:17. I'll be looking at the chat, so if you have any questions too, I'll answer them there. Okay, I'll see you in 10. Okay, so we're gonna come back. I'm stuck on the easy part of the proof, which is bugging me. I got the hard part here, and now I'm stuck on the easy part. Okay, let me just write out what I have, and then maybe somebody else will see what I'm missing. I actually swear I remember doing this part a couple of years ago. Now that I've started doing it, I'm like, oh yeah, I did this a couple of years ago. And then there's like a really easy fix to this, but I don't remember how I did it. So maybe I'll show you what we want to do. And maybe, like I said, somebody will see the easy thing that I'm missing. Okay, so what do we want to show? So basically we want to show that the infimum of u f plus g p is equal to the integral of f plus the integral of g, right? And the reason for that is that thing on the left-hand side is the integral, right? Because we know that f plus g is integrable. So this thing, and I'm going to write it in a different color here because I don't want us to confuse it. This thing is the integral of f plus g, right? Because we know it's integrable, so that is the integral. And then this is the identity that I want to show. But the reason I've written it like this is precisely because we're going to use the epsilon definition of the infimum, right? So we're going to say let epsilon greater than 0 be given, or maybe let me translate that. So we want to say for all epsilon greater than 0, there exists a partition P such that the integral of f plus the integral of g is less than or equal to u f plus g p is less than the integral of f plus the integral of g plus epsilon. Okay, so if we can do this, then that will prove that the integral of f plus the integral of g is equal to the infimum of these upper sums, and that in turn will prove that the integral of f plus the integral of g is the integral of f plus g, right? So that's what we want to do. Now, normally, so there's two inequalities that we have to prove here. Normally, the right inequality here is the hard one to do, and it's the one that I can do no problem, but the left inequality is usually the easy one, and it's usually it's the one that I can't, for whatever reason, see. Okay, so let me do the hard proof, and then again, if you see the easy proof, just yell at me. All right, so what we're going to do here is say the following. So again, we know that f and g are separately integrable. So since the integral of f is the infimum over all partitions of UFP. I should say let epsilon greater than 0 be given, sorry. So let epsilon greater than 0 be given. Okay, so since the integral of f is the infimum of the upper sums over f, there exists a partition, let's call it P1, such that the integral of f, maybe this will just work, less than or equal to UFP, maybe not, less than the integral of f plus epsilon over 2. And then since, same thing for g, right? We're going to do the exact same thing. Integral of g is the infimum over all the partitions of UGP. There exists some partition P2, such that same thing. The integral of g is less than or equal to U. GP is less than the integral of g plus epsilon over 2, right? Now, we know that for every partition P, UF plus GP is less than or equal to UFP plus UGP. So take P to be, again, P1 union P2, right? Again, both 1 and 2 hold. For P. And what do we get? So we're going to get that U F plus GP is less than or equal to U FP plus UGP. And now if I use 1 and 2, so that's going to be less than the integral of f plus epsilon over 2 plus the integral of g plus epsilon over 2. And that's exactly what we want for one side, plus the integral of g plus epsilon, right? So that's exactly, what did we just show? So we just showed that thing right there, right? So that's the hard one. And now it's the other side that oddly enough is giving me trouble. So I think I'm going to have to use L, and I really don't want to. Okay, so let's say if I use the lower sums, so I get the integral of L is greater than or equal to the lower sum over F. The integral over G is greater than or equal to the lower sum over G. I remember there's just like a one-line thing here. And it's just like, yeah, it's obviously true, but I can't quite remember what it is. Why is F plus G obviously bigger than the integral of F plus the integral of G? Yeah, I don't remember what it is. I'm gonna have to play with it a bit, everyone. So this proof temporarily is gonna remain unfinished just while I figure out what it is. And then on Thursday, hopefully I'll do it, because I don't want to like sit here for the next half an hour and try and think about what it is. So like I said, if anyone sees it, please let me know. Otherwise, I'm going to move on. Yeah, why? That's the hard direction. Why can't I think of how to do the easy direction? Damn, I wish I kept my notes. See, I'm doing it this year. You know, last time I taught 157, I taught it in hand, like in person. So I just write my notes on like a piece of paper and then I throw the piece of paper out. And I'm hating it this year because there are a bunch of proofs that I like had to work out a couple of years ago. And now I don't remember how to do them anymore. And I have to work them out again. So note to you, if you ever say to yourself, oh no, I know this really well, I'll never forget it in my life. That's absolutely not true. Write everything down. All right. That's one of the most important lessons I've ever learned in my life. As well as you think as good as you think your memory is, it's never that good. Okay. So if you learn nothing else today, maybe that, yeah, thank you. But yeah, if you learn nothing else today, let it be that one. Okay. That's your lesson. No matter how good you think you'll remember something, you won't. Actually, I don't know if I've told you this. Unfortunately, it took me to like grad school to realize this. But what I used to do when I figured out in grad school, there were definitely a couple of times where this exact thing happened, right? So I remember I was taking a course in algebraic topology and we were talking about like the Seifert-von Kampen theorem. And don't worry about what that is. But basically, it's tricky and it's really tricky to use and use it to compute like fundamental groups and cohomology and stuff like this. I think it was fundamental groups. And it was really tricky to figure out how to use it. So I'd spent a long time, like a couple of weeks, really grinding out the details and figuring out how to use this theorem. And I said, okay, boom, I've spent a couple of weeks doing this now. There's no way I'll ever forget this, right? And so we go and we continue the rest of the course and it comes time to study for the final exam. And then I realized, nope, forgot it all. And now have to relearn what I spent a couple of weeks teaching myself, you know, way back at the beginning of the year. And obviously it comes back quicker the second time, but I still had to reteach myself. So at this point, I said, okay, this was stupid of me. What I should have done is written down what I had learned, right? And in particular, written a letter to future me, explaining, like teaching future me the stuff that I had learned, right? So I learned it. I understood it really well at that time. I figured I couldn't forget it. But what I should have done is written a letter saying, future Tyler, this is the idea. This is how the theorem goes. This is how you compute stuff. These are the examples that really gave you trouble. These are the concepts that you struggled with, and here's how you got past them, and these sorts of things, right? And so I realized that, and the next time I took a course, I did exactly this. So once I learned something, yeah, no, I mean, like I would just try and remember everything, right? Like, so what I'm saying is I wouldn't write a letter to myself in the future. Like I would take notes, but I wouldn't write down a letter to myself. Explaining and reminding myself what were the things that I had really a lot of trouble with. So I started doing this in grad school. Like I said, it was stupid of me that it took me to grad school to do this. But yeah, I started to do that. And again, I would do it as if I were explaining it to myself again, right? If I had to teach myself at the beginning of the year how to do this stuff, how would I have done it? And then when it came time, so I did this, you know, in the follow-up course. And when I did that, again, you know, I'd forgotten everything when it got time to the final exam, but then I would read my letter and it came back almost immediately, right? There were a couple of exercises that I had to do because I'd recommended them to myself, right? Past me recommended it to future me. And like, do these exercises. These are the ones that really helped you make a difference. And I wrote solutions to them hidden somewhere, so I couldn't look at them, but I could check my work after. And yeah, I mean, it went from being something that might take 2 weeks for me to have learned the first time. And then when I would study for it, it would take a couple of days to relearn all that stuff. But instead it came back like within a couple of hours. So that thing of writing notes to yourself about what you struggled with and all that sort of stuff, like made a huge difference to my studying. And like I said, I didn't figure that out to grad school. So Sophia, if you're in a much better place than me, if you like have figured that out already, but yeah, like totally, that's a worthwhile thing to do. I explained that to my wife once and she just said, she started laughing at me and I said, what, do you think that's a dumb idea? She's like, no, I know that's a great idea because of how stupid it sounds. Because I described it as, you know, write future you a letter. And she's like, no, I know that's exactly a great piece of advice because it sounds dumb. And I said, thanks, honey. Like that really makes me feel good. But anyway, so that's, like I said, that actually really worked for me. So if you're one of those people, especially in a year-long class, because, you know, so much of the stuff that you might be covered on in the final exam is stuff you learned back in October. There's no way you're going to remember 6 months later, 7 months later, the stuff that you learned in October, right? So especially in a year-long class, doing that is really, really a good idea. And now maybe you're cursing me. You're like, well, why didn't you say that at the beginning of the year? It's now halfway through the year. Well, I don't know. It didn't occur to me. We had other problems, right? Yeah, exactly. Yeah. And I mean, you don't have to be like, dear Tyler, I hope things are going well. And if not, here's how you can remember how to do this there. Don't do it like that. But I write it, like I said, as if I'm writing a lecture for myself. And because nobody explains to you better than you do, right? You know exactly how your thought process works. You know exactly how that goes. So you should do that. Can we let u f plus g greater than or equal to something plus something since the integral of f? Okay, wait. There's so much math in the chat is tricky for sure. Can we just say like f plus g minus f less than? Yeah, I was thinking that. Does that work? Because the only problem is you've got that. Okay, so for Nicole, yeah, your only problem is you've got that like minus epsilon there, right? So can we just be like, yes, immediately, though we don't care because, yeah, it's the minus epsilon. Because I just want the integral of f plus the integral of g. And that's going to be bigger than the integral of f plus the integral of g minus epsilon, but we don't know really where it occurs in that chain, right? So yeah, that's a good idea. It's just that kind of leads us right. And then Stephen, can we let greater than u something plus the integral of f plus the integral of g is the soup? Yeah, it might. I feel like there is something along these lines that we can do that will work. Though I feel like it might have even been easier than both of what you're suggesting. Like I said, let me think about what you guys are saying, and I'll see if I can come up with it. And if push comes to shove, I'll do it on Thursday. Because yeah, I don't think I'm going to figure it out right now. While I'm also trying to figure out what I'm going to talk about in the right now, right? But yeah, no, keep those in mind. And again, if any of you guys can figure it out, that's great. And you can send it to me in an email or on Discord or on Piazza or something, and I would love to see that. Make me very happy. Yeah, okay, yeah. There might be something we can do there, Nicole, where you say, like, because it's true for all epsilon, effectively, it's true. There might be something we can do. Again, it's a little bit tricky because you still need your inequalities to work out, right? And that's the tricky bit there. But it's definitely along those lines. So see if you can do a full write-up of it, right? If you think that will work, just do a full write-up of it, and then you can email it to me and I'll take a look at it. Yeah, okay, but I want to move on now. And like I said, though, it's not to shoot down anyone's ideas, but if you think that it will work, do a full write-up of it to me, and then you can send it to me. And I will give you full credit if I do it on Thursday. I'll be like, yeah, this is Nicole's idea or Stephen's idea. But yeah, let me take into this next thing, because there's actually a fair amount that needs to be done here. We need to start talking about measure. Now, this is going to be a little bit weird. We're going to step away from integration for a second, just for a little bit, like the rest of today and hopefully Thursday. And then we're going to come back in, because I need the word measure. I need you to all know what measure zero means, for example. Okay, and so we've got a big definition in front of us. Big definition. All right, so if I is equal to the open interval AB, we're going to define the length of I to be B minus A. Okay, that's not crazy. So you're given an interval, the length of that interval is the length of the interval, right? A polyinterval is a finite union of disjoint intervals, disjoint bounded intervals. Okay, so important points is, let me underline in a different color, finite union of disjoint bounded intervals. Okay. I1 union I2. So basically, it's a finite union of the things that look like I above there. The length of that polyinterval is the sum of the lengths of all of its constituent intervals. the length of P is let's just write it like this. Let's not use a sum. Like that. Okay. By convention, we'll say that the empty set is a polyinterval and its length is 0. Okay. All right. Still not at the bad part. All right. So if S is bounded, we define the outer measure this is technically the outer Jordan measure as mu star of S is the infimum of the following set. So it's the infimum of the lengths of all the polyrectangles which cover S. Okay, and the inner measure same thing, but it's going to be the supremum over the polyrectangles contained in S. Right? Should feel a little bit like integration. So what we're saying here is use a polyrectangle, which is just, again, a disjoint union of finitely many bounded intervals. So use those things whose area we know, right? Just like rectangles, we know what the area of an interval should be. Now cover that your set with those polyintervals, or sorry, polyrectangles. Or have I been calling it polyinterval or polyrectangle? Oh, sorry, this should be polyinterval. Rectangle is what you use in higher dimensions, right? Okay, so you over approximate the area. And the Jordan measure says, once you've over approximated the area, take the infimum over your over approximations. The inner measure is you under approximate the area, right? So you look at the polyintervals which live inside of your set, and then you take the supremum of those. So those are all under approximations, and then you take the best under approximation. And then you can probably guess what's coming up. A set is said to be measurable if those two things are equal, in which case its measure is either of those numbers because they're equal. So S, a set S is measurable if the outer measure is equal to the inner measure, in which case its measure is either of those numbers, right? Because they're the same. Okay, and then a set is said to be measure 0 if it's measurable and has measure 0. Right, so you can say measure 0 or 0 measure, doesn't matter. I feel like if I recall, measure 0 sounds weird the first couple times you say it, but like it eventually grows on you. Has measure 0 if it is measurable and its measure is 0. Okay. So again, should have some sort of feeling like integration, sort of. And basically what we're doing is we're trying to figure out what the measure is what is the length of a general set. So if you're given an interval, you can probably guess it's, intervals are measurable, or bounded intervals are measurable, and their measure is exactly their length. The more interesting question is what happens when you have weird sets, right? Like what if you have like a finite set, or a set that has some interval parts and some finite parts, or the rationals. What's the measure of the rationals in 0, 1, or something like this, right? So this is for dealing with weird subsets of the real numbers. The nice ones, we can probably guess what their answer should be, but this is formally how we're going to deal with the nasty sets. Okay. And we do the same thing as with integrals. We over approximate the area and take an infimum. We under approximate the area, we take a supremum, and it's measurable, i.e. we can actually determine what its area is if those two numbers are equal. Can we fix weirdness with polyintervals? What do you mean? Yeah, in the sense, yeah, what do you mean by fix, and what do you mean by weirdness? So the answer is maybe yes, depending on what you mean by it. Yeah, exactly. Yeah, that's exactly what it is, right? Yeah, so here, maybe we can draw a picture. So like, here's the real number line. And maybe you have something, so here's gonna be my set S. I'm gonna draw it in blue. And then maybe it's got a couple points here like this, right? And then maybe, it's got another interval. And then maybe it's got like a cluster of points right here. So these points are all distinct, but they're, they kind of cluster together. And yeah, exactly what we're going to do. So let's do the outer measure. Most times you want to do the outer measure. It's sort of the nicer one to do. So if we take the outer measure, we might take something like, here's what my polyrectangle is going to be. So just to remind you, S is the blue set. So our polyrectangle might look something like this. Right, and it could be bigger, but sort of like you can see here that this is trying to approximate the total length of this set, and that's the sort of idea of what's going on here. Is the U in U? Yeah, that's a mu. Yeah, exactly. That's my mu. Yeah, let me see if I can exaggerate that mu a little bit more. So mu like that. Yeah, if you just want to use an M, it's okay. Okay. As a word of casual warning, we're not going to use it in this class. Depending on what books you use in the future, I've mentioned that there's a difference between Lebesgue and Lebesgue and Jordan measure. This is purely for your interest. We're not going to do this in this class. If you want to do Lebesgue measure, okay, and Lebesgue is sort of the proper one that you would do in a more hardcore analysis class, right? What's more hardcore than this? They do exist. Lebesgue does not require that you take a union of finitely many polyintervals. For Lebesgue, it can be countably many. So here, in this part here, this can be ... and you can have countably many. Not even in 257. Even in 257, we talk about Jordan. I know at St. George, they do Jordan as well, right? Because it makes a big difference when you do put the ... there. For outer measure, is S a subset of P or P is a subset of S? Oh yeah. Oh man, did I write these backwards? Okay, hold on. So S should be a subset of P, and here P should be a subset of S. I don't know if I got those backwards. Yeah. Okay. No, this is very interesting. So Summon, like, great question. No, there are definitely infinite sets that have measure 0. Yeah. So you can probably, you've got a good guess so far that finite sets probably have measure 0, but there are also infinite sets with measure 0. And with Lebesgue, there are a lot more, okay? So if you want to change it to Lebesgue, which we're not going to do in this class, the thing that I've circled here can have countably many polyintervals, or it can have countably many intervals inside of it instead of just finitely many, but that makes a big difference, big difference, changes everything. So that's number one. There are 2 or 3 different definitions of the measurable. They're all equivalent, but there are a couple of those as well. And then some authors say 0 content, or sorry, the content is the Jordan measure and measure is Lebesgue measure. So if you have 0 content, then that means you have Jordan measure 0. And if you have measure 0, that means you have Lebesgue measure 0. Okay, so just sort of like a difference in terminology. That's not even consistent from author to author, but you might come across that at some point in the future. Okay, so let's kind of prove, yeah, I can prove something quick here. So proposition for any S, really for any S, but let's say for any bounded S, we're always going to be dealing with bounded sets. For any bounded S, the inner measure is less than or equal to the outer measure, right? So that's not crazy. Proof of this. Do I think, oh yeah, I did want to do that. So let's say define I to be the inner polyinterval, sorry if I keep saying polyrectangles, such that, actually, do I want the, such that P is contained in S. And again, hopefully you know it's a polyrectangle, don't make me say it. And O to be the covering polyrectangles, right? Okay, so for any, let's say P in I and Q in O, we have that, I guess I should write the norm of P or the length of P. We have the length of P is less than or equal to mu star S. Maybe that's not how I want to do it. Right. Damn, what do I want to do here? No, let's take the norms off the inner and outer. I'm sorry about that. So for any P in I and Q in O, we have that P is contained in S, which is contained in Q, right? So in particular, Q is a polyrectangle cover of P. Right, is that how I wanted to do it? Yes. So thus, the norm of P is less than or equal to the norm of Q. And that means that the sup of the norm of P is less than or equal to Q, which implies that the inner measure is less than or equal to Q, and that this is true for all Q. This holds for all Q in O. Okay, and then in turn now, if I take the infimum, Q is from O. Yeah, maybe let me write that. Q is in O, and O is this thing right here. Right, O is like the outer things. So I is for the inner polyintervals, and O is for the outer polyintervals, right? The things that like cover our set. Right, so basically all I'm trying to argue here is that everything in O is, when you take its length, is an upper bound for the interior polyintervals. And therefore, when you take the supremum, you actually get that there are upper bounds for everything. And then similarly, I'm going to now take the infimum over all the Qs, and that's going to give me the inequality that I want, right? All right, so thus mu star S is a lower bound. For the lengths of Q, and that means that it's less than or equal to the greatest lower bound, right? The infimum. So mu star S is less than or equal to mu star S. Just the definition of the set O, we don't need Q in there. What do you mean? So yeah, O is the collection of polyintervals which cover the set. And I'm saying let Q be any such polyinterval. Right, that's why, yeah. I was messing around with that definition a few times, so maybe that's what threw you off. And that's why this is true, right? Because my interior polyrectangle or polyinterval is inside of S, And then Q is my outer Pauli intervals. That's why S is contained in int. And then this allows me to deduce that this is true. And then basically it's back to our usual sort of like upper and lower sum argument, which is once you know this is true, right, that the length of all the inner Pauli intervals is less than the length of any outer Pauli interval, then, well, that must also be true if you take sups and nams, right? And that's basically the argument. So voila, we have it. The inner measure is always less than or equal to the outer measure. We're just about out of time, so let me leave you with a very easy proposition, which I want you to prove. I will do it on Thursday, but you know, this is something you can do. So if S is a subset of R and the outer measure is 0, then S is measurable. And the measure of S is 0. Okay, very easy proposition. Should be like 1 or 2 lines to prove. So let me leave you with that and see if you can prove it. And then, yeah, I'll try and fix the sum of that, the sum of the integrals thing, which is bugging me. Yeah, it's the easy proof. I can't believe I don't have it. Okay, so I'm going to leave you that. Try and do it. Seriously, you should be able to do it in 1 or 2 lines. It's very straightforward. And then when we come back on Thursday, what do I have in store for you? A little bit more measure stuff. It's actually just all measure, I think, for the rest of the week. And then next week, we'll go back into integration, and that's when we'll do our integrability theorems and talk about all the sorts of things which are integrable. And so we don't have to do things by hand anymore, right? That's the idea. Of course, we have to prove stuff though, but what are you going to do? Okay, any questions? Everyone's good? Let me know. What is that phantom P? Oh yeah, okay. All right, everyone's good? Works for me. And again, if you have a question and you're still typing it up, no problem, just keep typing. Otherwise, well, we'll test 4 cover. When is even test 4? Are we at the point where we should worry about that? Test 4, everything up to and including the end of next week, right? So usually you know the cutoff is the week before. So it looks like test 4 is on February 4th. So that means it will cover everything up to and including what we do next Thursday. So all of this week and all of the week following should be the material. Okay. And yeah, let me just double check that it is on February 4th. Otherwise, I'm very worried. Yes, it is February 4th. Good. Okay. All right, everyone. Thank you for coming today. That we're going to finish there. Yeah, thank you. And I'll see you bright and early on Thursday. Okay. Bye, everyone.